Today, lesson 35b, the Pythagorean Theorem. We've been working a lot with square roots and how to simplify or estimate square roots. And today is an application of one of those things. And the Pythagorean Theorem, one of the most famous theorems in mathematics, and it allows us to find the missing side of a triangle if we know two of the other sides. So, a long time ago, a Greek mathematician named Pythagoras discovered an interesting property about right triangles. The sum of the squares of the lengths of each of the triangle's legs is the same as the square of the length of the triangle's hypotenuse. That's a lot of writing there. This property, which has many applications in science, art, engineering, and architecture, is now called the Pythagorean Theorem. And the Pythagorean Theorem works like this. If A and B are the lengths of the legs of a right triangle and C is the length of the hypotenuse, then the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. This relationship is represented by the formula a squared plus b squared equals c squared, and that is Pythagorean Theorem. So where does A, B, and C come from? Well, before I quickly talk about that, this relationship between A, B, and C, it only works for right triangles. I don't want you to think it works on all triangles. So if we have a typical right triangle, which you should recognize from probably 5th or 6th grade, the two parts that make up the right angle, those are called legs. That other side that's directly opposite the right angle, that is what is referred to as the hypotenuse. And we typically use A and B for the legs and C for the hypotenuse. And one other quick note here, and if that's not written down in your notes somewhere, you may want to write this down. That I already mentioned that the hypotenuse is opposite the right angle, but the hypotenuse is always the longest side. And when we're checking things with the converse of the Pythagorean theorem, we need to keep that in mind. The hypotenuse is always the longest side. So putting this to use, once again, we usually utilize the letters A and B for the legs and C for the hypotenuse. Now it is okay to interchange the A and the B, just as long as A and B are always the legs. So the vertical leg could be B instead of A. You could always flip-flop those two. But once again, they are interchangeable. But the Pythagorean Theorem, the relationship between those three things is a squared plus b squared equals c squared. All right. Let's start with number one. Using a squared plus b squared equals c squared, 6 is either a or b, 8 is either a or b, but c has to be the variable x. So if we utilize the Pythagorean Theorem, we substitute those things in, and now we have something that we have solved before. I would like all of you to finish solving number one. So let me go through here. 6 squared is 36. 8 squared is 64. We're just following the order of operations. 36 and 64 is 100. We have solved equations like this before, and I just asked the question, why not negative 10? Yeah, we don't have a negative side of a triangle. So if it's just solving the equation, we've got to remember the plus or minus thing. But for sides of a triangle, we just take the positive part. So the missing side of that triangle is 10. All right, let's go to number 2. Find the missing side of that right triangle using the Pythagorean Theorem. Remember, that's what the Pythagorean Theorem is for. If we know two sides of any right triangle, we can find the third side using the Pythagorean Theorem and that relationship between A, B, and C. All right, so it doesn't matter whether A is 4 or A is 7. Just make sure that 4 and 7 are the legs. Therefore, they have to be A and B. So we have something like this. 7 squared is 49. 4 squared is 16. Add those two together. Take the square root of both sides, and we end up with the square root of 65. Now, typically, if we have a radical that can be simplified, we should simplify it. However, square root of 65 is already simplified. The other issue is if it's not a perfect square, we should also estimate to the nearest tenth. Now, based on what I saw on the last quiz, most of us have no problem with that. So can I cut out some time right now and just give you the answer estimated to the nearest tenth? Yes? We all know how to do that? Okay, it's approximately 8.1. So you'll always need to redirection. Sometimes it may just say simplified radical. Sometimes it may say, you may have directions that tell you to simplify to the nearest tenth. And we have learned different methods of doing that. All right. Easy when you have both legs, but what if you now are trying to find a leg? So what would the setup look like on this one? What would it look like? Mason? Yeah, that 15 is the hypotenuse, so therefore it needs to be by itself. I'm going to go with, you said 6 squared plus t squared. I'm going to take it as t squared plus 6 squared. It doesn't matter. You can interchange the two legs, but that 15 squared has to be over there. All right. You should know enough to go ahead and finish that one. Continuing on here, 6 squared is 36. 15 squared is 225. Subtract 36 from both sides. Remember, we need that variable squared by itself. Now take the square root of both sides. The square root of 189 can be simplified to 3 square roots of 21. And then to the nearest 10th place would be approximately 13.7. Any questions on number 3? Okay, everybody try. Number 4. So utilizing the Pythagorean theorem, we may have something like t squared plus 1 squared equals square root of 7 squared. 1 squared is obviously 1. Square root of 7 squared is square root of 7 times square root of 7. And if you didn't realize that that was just 7, square root of 7 times square root of 7 is square root of 49. And square root of 49 is, once again, just 7. Subtract 1 from both sides. And we end up, after we take the square root of both sides, with simply the square root of 6. That cannot be simplified, but to the nearest tenth, that would be approximately 2.4. Questions about number 4? All right, let's go on to number 5. Everybody try number 5. Pythagorean theorem says leg squared plus leg squared equals hypotenuse squared, or a squared plus b squared equals c squared. The legs are t and 3 square roots of 2, and the hypotenuse is 7. There seems to be a bit of an issue with a few of you with this right here. So let me go ahead and take care of the easy parts first. Just off to the side, 3 square roots of 2 squared means, the long way, 3 square roots of 2 times 3 square roots of 2. This is one of the reasons why we worked on that last week, multiplying radicals together. We can multiply, one way of thinking about it is we can multiply non-radical times non-radical and radical times non-radical. And once again, this is the long way of getting there. 9 times the square root of 4 is 9 times 2, and that is 18. So that means that the square root, or excuse me, 3 square roots of 2 squared is 18. That's what this side squared is, 18. And then from there, we would subtract 18 from both sides and take the square root of both sides. Square root of 31 cannot be simplified, but to the nearest tenth is approximately 5.6. So any questions on 1 through 5? And yes, we do need to know how to do it even when sides of a triangle have a root in them. Okay, so that's the Pythagorean theorem. Now, the converse of the Pythagorean theorem. The converse of the Pythagorean theorem is basically the flip of it. So for any triangle with sides A, B, and C, if a squared plus b squared equals c squared, then the angle between A and B measures 90 degrees, and the triangle is a right triangle. So what in the world does that mean? Well, that means this. If we have 3 sides of a triangle, like 5, 12, and 13, the question is that a right triangle or not? The only way to figure that out is to utilize the Pythagorean theorem. Now, when you're doing that, what we need to make sure that we realize is that one of those has to be the hypotenuse. Which of those sides must be the hypotenuse? And if you were listening at the very beginning of the lesson, it should be obvious. Which one? 13. It's always the longest? Good. Therefore, it has to be the hypotenuse. And at that point, it doesn't matter whether you put 5 here and 12 here, or 12 here and 5 here. It doesn't matter. But we need to check with the Pythagorean theorem. So I would like you to do that on both 6 and 7. So basically what you're trying to figure out is, can those three sides make a right triangle? You use the Pythagorean theorem to test it and figure it out. If it makes a true statement, it's a right triangle. If it does not make a true statement, it's not a right triangle. It still might be a triangle, but just not a right triangle. And a reminder, once again, that the hypotenuse is always the longest side. And once again, you should be doing both number 6 and number 7. All right, so number 6, 5 squared plus 12 squared. That is 13 squared, and I'm proving it right there, so that means that that is a right triangle. And in number 7, we need to make sure that 12 is the hypotenuse. And when we check with the Pythagorean theorem, this does not make a true statement, as you can clearly see. So therefore, this might be a triangle, but it's certainly not a right triangle. All right, so now a couple of word problems where we utilize the Pythagorean theorem. Before we get to that, there are some special right triangles that involve, thank you, numbers that we sometimes call Pythagorean triples. And if I were you, up at the top of this side of your notes, I'd write some of these down. So 3, 4, 5, one of the most common right triangles. Okay? 3, 4, 5. So that makes a right triangle. 3 squared plus 4 squared equals 5 squared. But also multiples of those numbers. So if I took and doubled each of those numbers, that also makes a right triangle. 6, 8, 10, that's just 3 doubled, 4 doubled, and 5 doubled. Or if I triple each of the 3, 4, 5, that's another right triangle. So there are lots of right triangles that are created from 3, 4, 5. So 3, 4, 5, one of the most popular ones. The second most popular one is probably 5, 12, 13. Or multiples of those numbers. If I double each of them or triple each of them and so on. So all of these right here, those 10, 24, 26, 15, 36, 39, that's just based on a 5, 12, 13. Probably the third most popular Pythagorean triple is 7, 24, 25. Or multiples of those numbers. And probably the fourth most popular Pythagorean triple is 8, 15, 17. Or multiples of those numbers. Now, there are many more Pythagorean triples. But these are the 4 most popular. Now, some of you might be thinking, well, why in the world are you giving me those? Well, here's the reason why. Sometimes, if it's sometimes we have problems where we don't even need to utilize Pythagorean theorem. We can just see it from one of these 4 Pythagorean triples. And here's one. What if I gave you that triangle right there, where one of the legs was 60, the hypotenuse was 65? What's that other leg? It's based on one of the Pythagorean triples that are right up there. I'm going to give you about 30 seconds, and then I want you to talk about that with your shoulder partner. Obviously, we could just use Pythagorean theorem. That's perfectly acceptable sometimes. We could save a little bit of time if we try and see if it's based on a Pythagorean triple. What's the missing side? What is it? 25. So which Pythagorean triple is it based on? 5, 12, 13. Very good. Now, there are lots of different ways you could get there. One of the things that I try and do is I look at the two sides that are given here, and I think about, well, what's the greatest common factor between those two numbers? What's the biggest number that goes into both those evenly? It's 5. What's 60 divided by 5? It's 12. And what's 65 divided by 5? And sometimes that helps us look and see at what we're trying to find here. So if the hypotenuse is 13 and one of the legs is 12, so we're basically trying to figure out, well, what number, when I divide it by 5, will be 5, and of course that's 25. So just another way of attacking some of these triangle problems. All right, number 8. A car drives 10 miles due east and then 24 miles due south. Due means straight. So 10 miles due east, sometimes it helps drawing a picture. 24 miles due south. To the nearest hundredth of a mile, how far is the car from its starting point? This was its starting point. This is where they are now. You're trying to figure out how far is it from there to there. Obviously, this is a right triangle. Find out how far they are apart. Or find out how far he was from his starting point. All right, utilizing the Pythagorean theorem, if you didn't see that this was based on a Pythagorean triple, you could just use the Pythagorean theorem. 10 squared plus 24 squared is 100 plus 576. That's 676. Take the square root of both sides, and that is 26 squared. So it is 26 miles from the starting point to the end point. All right, let's continue on. Number 9, to the nearest tenth of a foot, find the length of the diagonal of a rectangle with the width. So you probably should draw a picture like the last one. The width is 4 feet. The length is 10 feet. You're trying to find the length of the diagonal. And if you couldn't tell by the wording, you basically have, if you think about it right here, you have a right triangle. All rectangles are 90 degrees in the corner. Find how long that diagonal is. Okay, so Pythagorean theorem, a squared plus b squared equals c squared. We've got 4 squared plus 10 squared equals x squared. That's 116 equals x squared. Take the square root of both sides. By the way, that can be simplified to 2 square roots of 29. And to the nearest tenth, that would give us approximately 10.8. And of course, that should be feet, since we're talking about sides that are have a length in terms of feet. All right, number 10. Now we take the Pythagorean theorem to 3 dimensions. Here we have a prism, a rectangular prism. And we're trying to figure out the longest aluminum pole that you could fit in that box if it went from one corner down to the lower corner. So that's represented by that red line right there. Well, in order to do that, we would basically have to do the Pythagorean theorem twice. And what I mean by that is I can't find this side right here unless I know that side right there and this side right here. But fortunately, I already know that. If this is 3, it's also 3 here. So I need to figure out what this side right here is first. So I would need to do the Pythagorean theorem on the bottom of this prism. If it's 2 here, it's 2 here. So right here we have this right triangle that has one leg that's 2 and another leg that is 4. So let's kind of go through that together. All right, so basically I've just filled in all the areas that I just talked about. So in order to find that diagonal across the bottom of the box, we would have 2 squared plus 4 squared equals c squared. And that would be the square root of 20. Obviously, we don't take into consideration negative side, so I don't need the negative there. And so that means that diagonal is the square root of 20. Now we're going to do the Pythagorean theorem again, because now we have this right triangle right here, where one leg is 3, the other leg is square root of 20, and when I solve for the hypotenuse there, that gives me the length of that aluminum pole. And so now I'm going to do the Pythagorean theorem again, right there for that right triangle, and I end up with the square root of 29, or approximately, and I don't know why I went out so far here, we're going to round that to the nearest tenth. That would be 5.4. And are there any dimensions? Yes, feet. 5.4 feet for that pole. Pythagorean theorem twice. Now, we could utilize the Pythagorean theorem twice every single time. But for 3 dimensions, there is... Oh yeah, let me go backwards here for a second. I wasn't even paying attention to what I was doing there. I said it was 5.4 rounded to the nearest tenth, but notice my answer there is 5.3 feet. Why is it 5.3 instead of 5.4?
It's asking, like, how can you fit it in a box?
Yeah, if it's 5.4, that's longer than this side right here, so that means 5.4 actually won't fit in the box. So I would need to round actually down in that part right there. So make sure we're paying attention to that. All right, so in 3 dimensions, here is a formula for finding the length of something like an aluminum pole. And it's really just based on Pythagorean theorem. So if I did Pythagorean theorem once, based on the sides I have right there, to give me that diagonal across the bottom of the box, that would be square root of L squared plus W squared. And now if I did the Pythagorean theorem again, look what we end up with right here. The diagonal squared, which is basically that right there, is the length squared plus the W plus the width squared plus the height squared. This is just an extension on the Pythagorean theorem in 3 dimensions. So if we took the square root of both sides, this might be a better one for you. This would always give you the length of that diagonal from one upper corner of a box or a prism down to the lower opposite corner of the prism in one formula. And once again, it's just based on the Pythagorean theorem twice in 3 dimensions. All right, that is it for today.